All right, so today we're gonna go in. We learned the empirical rule so far, and now we're gonna go in and talk more about normal distribution. So this is the second part of Unit 6C. All right, so normal distribution is a bell-shaped distribution. All right, so it looks like a bell. It has a single peak. Its peak corresponds to the mean, median, or mode. So, this. All right, so the peak is the average. All right, so right in the center corresponds to the average, which can be the mean, the median, or the mode. Most commonly it's the mean, but it could be any of them. All right. So basically this is called the normal distribution, or they call it a bell-shaped curve. Which just means it's a normal curve. All right, what is normal? What does it mean to be normal? That's a question many people have been wondering in their lives. All right, so basically we're just talking about that it means that most of the data values are clustered near the average, or usually it's the mean. I'll say average. And then I'll say usually mean, or in parentheses. Given it a well-defined single peak, data values are spread evenly around the mean or about the mean, making the distribution that looks like a bell-shaped curve. Now, as you go away from the mean, deviations from the mean, right, as you go away from it, become increasingly rare. So as we go farther and further away, or larger deviations away from the mean become more and more rare, right? If I think about right here there's a lot of data right here. Whereas if I go further and further away from the mean, there's not much data. So larger deviations from the mean are increasingly rare, and then that produces tails, right? This is a tail on this side, a tail on this side, right? We have tails of the data. Individual data values result from a combination of many different factors. So it just depends on what you're talking about. It could be talking about, the genetics of a person. I don't know. In this example we're about to talk about in a minute, it's more about genetics. And then the other example is about environmental. Factors. But it really just depends on whatever the data set is representing. So, example 1, the figure below shows two distributions. A famous data set of chest sizes of 5,738 Scottish militiamen collected in about 1846. So this has to do with more genetic. And then the second one is the distribution of the population densities of 50 states. So maybe that has to do with more environmental factors, right? Depending on the state, if it's a desert, you probably don't have a huge population. Well, maybe you do, I don't know, but maybe it's spread out over a smaller area, right? Or if you have a lot of canyons, people probably don't live in that canyon. So environmental factors, right? It says is either of these a normal distribution? Well, I mean, if we draw a curve to kind of go with this, we can see, yes, this is a normal distribution. Whereas this one, it comes up and then it tapers off. This one would be skewed to the right, because the tail is on the right side. So it tells me it's skewed to the right. All right, so let's continue this normal distribution. So, because all normal distributions have a bell-shaped curve, right, the same, you can characterize the variation of any normal distribution by the standard deviation. So that's one of the big points of standard deviation. All right, recall that a standard deviation gives the measure of the average spread of the data, right? A simple rule, right, is the rule we talked about in class today, the empirical rule. And it gives some, precise guidelines for percentages of data that lie 1, 2, and 3 standard deviations away from the mean. All right, so that's what we talked about in class today. All right, so let's kind of review that real quick just so you are with me. So when you're doing a problem, here's what you should be kind of doing. So a survey finds that the prices paid for 2-year-old Ford Fusions are normally distributed. So right when I see that word, normally distributed, or maybe I see it has a bell-shaped curve, I'm going to go ahead and kind of sketch that out real quick. All right, so it's supposed to look good. Mine, it ain't great, but it'll be all right. And then it says it has the mean of $17,500. So right in the middle, I'm saying $17,500. And then it has a standard deviation of $500. So based off the empirical rule, right, which is also the 68, 95, 99.7 rule, same thing as the empirical rule, I should go 1, 2, 3 standard deviations above and 1, 2, 3 standard deviations below. Matter of fact, I'm going to space it out a little bit more. So 1, 2, 3 above and 1, 2, 3 below. All right. And since each standard deviation is just plus $500, I know that the first one above is $18,000. And then we got $18,500. And then I got $19,000. And then this one is $17,000. $16,500, right? $16,000. All right. How many people paid between 17,000 and 18,000? Well, that's 1 standard deviation below and 1 standard deviation above. Now, I know we're talking about that right there encases 68% of the data, approximately 68% of the data. So this is 68%. Now, in class today, we left it at that. But the question is going a little deeper. It says how many people, right? Let's go back to and see the sample size. They had a sample of 10,000 people. So we're saying 68% of 10,000. So 68% of 10,000 people would be 6,800 people. Right? All you got to do is just say 0.68, right? We convert it to a decimal times 10,000. So 0.68 times 10,000. All right. Let us continue. So question or part C says, how many people paid less than $17,000? So as we talked about in class today, we know that our curve gives us, there is 100% of the data, right? And then it tells us, I know 50% is above the mean and 50% is below the mean. So if I know this from here to here is 50%, and I know from let me change my color. From here to here is half of 68, right? Which is 34%. Then from, all the way this way is 16%. So how many people paid less than 17,000? 16% of people did. Of the 10,000 people, which is 0.16 times 10,000, which is going to give you 0.16 times. Yep, 1,600. 1,600 people. All right. It then says how many people paid more than $19,000. So, all right, here's what we know. $19,000 is 1, 2, 3 standard deviations above the mean. If I go 1, 2, 3 above and 1, 2, 3 below, then this amount of data right here is 99.7%. 99.7% of the data falls within 3 standard deviations below and 3 standard deviations above the mean. So we know all the data is 100%. So there's still 0.3% of the data left over out of 100, right? That means half of that is above the mean, or above 3 standard deviations, and half of it is below. So we have 0.15% above and 0.15% below. So how many people paid more than $19,000? Well, 0.15% of people, which really just means we're going to say 0.15, or I'm sorry, be careful. This is a percentage. So that would be 0.0015 times 10,000. .0015 times 10,000 gives us 15 people. Only 15 people paid more than $19,000 for Ford Fusion. 2-year-old Ford Fusion. All right. Hopefully that makes some good sense to you. I feel like that follows what we did in class today, but now we're going to move a little bit further on. So now we're going to start talking about what's called Z-scores or standard scores, right? So standard scores or Z-scores. All right, so the empirical rule, or the 68, 95, 99.7 rule, applies to the data values that are exactly 1, 2, or 3 standard deviations away from the mean. But what about when you have cases that they don't necessarily fall 1, 2, or 3 standard deviations away from the mean? All right, that's where the Z-score stuff comes in. So the standard score or Z-score of the data is a number that is the number of standard deviations a value lies above or below the mean. The number is often abbreviated by the letter Z. That's why they call it a Z-score. So here's how you can find the Z-score. The Z-score is equal to the data value subtract the mean divided by the standard deviation. Most of the time, you might would see it like the Z-score is equal to your X subtract the mean, which is X bar, divided by the standard deviation, like that. That's just the notation for it, but it means the same thing, right? So the Z-score of the mean is Z equals 0 because 0 standard deviation. If you have a Z-score of 0, that means it's 0 standard deviations away from the mean. Therefore, it is z-score of 0. If you have a z-score that's 1.5, it means you're 1.5 above the mean, right? Above. If you have a z-score that is 2.4 standard deviations below the mean, then notice the z would be negative 2.4. So when the z-score is positive, that means that we're above the mean or the average. And then when the z-score is negative, we're talking about below the mean or the average. All right, so let's look at a couple of these. It says the Stanford-Binet test, the Stanford-Binet IQ test is scaled so that scores are normally distributed with a mean of 100 and a standard deviation of 16. Find the standard scores or the z-scores for IQ scores of 85, 100, and 125. All right. So I like to get a picture of this, right? I always like to kind of start with the picture. So we got our standard curve, our normal curve, and it tells me it has a mean of 100. So 100. And then it has a standard deviation of 16. So if I take 100 and I add 16 to it, I get 116. If I do it again, I got 132. If I do it again, I got 148. So that's, 3 above. Now let me go 3 below. So 16 minus 100, we got 84. Then we got minus 100 again. Or I'm sorry, minus 16 again. So 84 minus 16 gives us 68. And then again, we got 52. So this is, just to be clear, we have our mean here, and then we have plus 1 standard deviation, plus 2 standard deviations, and plus 3 standard deviations. Here we got minus 1 standard deviation, minus 2 standard deviations, and minus 3 standard deviations, all coming from the mean. All right, so let's think about this real quick. Find the standard score for 85. So 85 means that I'm going below the mean, about right here. So that's not quite 1 standard deviation below the mean, but it's close. So that's kind of how it falls, but let's kind of get the z-score. So the z-score is equal to the data value, so 85, subtract the mean, so in this case, subtract 100, and then divided by the standard deviation, which is 16. So 85 minus 100 is negative 15, divided by 16, which gives you, really that's probably how we should give it, but negative 15 divided by 16, we can say the z-score is negative 0.9375. So that would be your z-score, negative 0.9375. So z equals negative 0.9375. You see how this is negative 1, but if we go 85, we're not quite negative 1. So, yep. What about 100? So, I'll change colors. We got the z-score is equal to 100 minus 100 divided by 16. 0 over 16, which is still 0. If I'm at 100, how far am I away from 100? I'm 0 away from it because I'm right on it. So the z-score 4/100 is 0 because that is also the mean.